Thank you again for the invitation. It's a pleasure to have the opportunity to tell you about what we do at the Institute of Neuroinformatics at the University of Zurich and ETH Zurich. And the goal was to present on brain-inspired electronic circuits for enabling neuromorphic intelligence in autonomous cognitive agents. It's a long title, but I would like just to emphasize the word neuromorphic and brain-inspired, and tell you a little bit about electronic circuits that can be used to emulate the brain and also build devices that can be used in practical applications, and that somehow are complementing artificial intelligence neural network accelerators. Let's see if it goes to the next page.
Maybe you can drag the slider from the side.
I only see the main. If I click on it, no. So maybe I have to ask you to go to the next. Oh, there it is. I see. I understand now. Yes. So the term neuromorphic, as I was saying, is related to artificial intelligence, but it's also related to neuroscience and biology and understanding how the computation in the brain happens. In fact, it's a term that embraces multiple communities. The term was coined by Carver Mead in the late 80s, early 90s to design circuits using subthreshold analog and asynchronous digital technologies for emulating the principles of computation in the brain. And it was really basic research. It was really trying to understand how the brain works by building, understanding by building. Of course, those were the times in which Moses was being sort of set up and VLSI was being made accessible to also universities. And so it was really a nice time for doing analog and digital circuit design using standard silicon processes, old processes, 2 microns and 1.2 micron, but still quite exotic in the sense that they were using analog circuits and not digital like the rest of the world. More recently, in the early 2000s, maybe 2005, 2010, another class of devices, VLSI chips, started to emerge that were designed specifically for simulating spiking neural network algorithms. So it's really not emulating with the physics of the circuits, the biophysics of the cells, but more at a higher abstract level, simulating algorithms of spiking neural networks. One of the first of these chips was the one proposed by IBM. It was the True North chip with the fully digital circuits, which were, however, using asynchronous communication. So also in that case, it was sort of exotic because it was not classical digital synchronous design flow techniques, and it was also spiking neural networks, which were and are still sort of not the standard way of doing neural networks in computer science. Another example is Intel. Intel has this Loihi chip, which is also being advertised as a research platform for simulating different types of spiking neural networks. And then, for example, in Europe, there was this huge project called the Human Brain Project that also supported and funded the design of spiking neural network chip designs and systems, mainly the Brainscale systems in Heidelberg and the Spinnaker system in Manchester. This is the sort of another community using the term neuromorphic. All these chips are called neuromorphic chips. And finally, even more recently, actually from 2008 on, but even more recently, the community of material scientists and engineers and physicists doing memory technologies started to use the term neuromorphic as well to refer to those devices that could be used as memory elements, but that could also do computation. And if you think of it in biology, the synapses in the nervous system are the site of storage. The synaptic weights are stored in the synapses, but they're also the site of computation because they're actually complex nonlinear molecular devices that have a very complex dynamics and processes going on whenever they are stimulated. So basically the term neuromorphic now is used to describe all of these communities. And the term neuromorphic intelligence is what we try to use to bridge across all these communities. So I will show you examples where we try to study really neuroscience. We study biology to understand how to do computation using neurons and synapses, but we combine analog and digital circuits, like it has been done in the, for example, Human Brain Project, to solve practical applications. So we want to apply these devices and these technologies to the real world, to solve real world problems. And we try to build systems that are compatible with these materials that are being designed for creating new types of memory technologies, for example, to replace flash, or to just create different types of memory structures that could be used in new types of processors. So this is the neuromorphic, the use of neuromorphic that is being done today. Now, if we go to the next slide, yes, I think this was the next slide. We should then realize that if we want to do computation using these principles of, brain-inspired computing technologies with new types of memory technologies using spiky neural networks, we really have to go away from the standard way of doing computing that is based on the von Neumann architecture, where typically you have a CPU on one side, you have computation on one side, and storage on the other. And in fact, if you think about it, what is being the major cause of problems in today's new types of computing devices is the energy consumption, and most of the energy consumption, 99.99% of it, is actually burnt by passing data through from memory to CPU and from CPU to memory. Computation is actually essentially free. It's very low energy, and what is really expensive is just sending data back and forth at gigahertz for just processing the data, getting the new state of the data, and so on. So if we really want to create a new type of technology that is much lower power, we can, for example, look at how the brain does it. And in the brain, there is this idea of co-localized memory and computation, as I was saying before, with the synapses. And this is not just a small change, it's really a radical paradigm shift. And if we want to really take advantage of all of the features of the brain, we have to really go away from this standard way of doing computing. So there are two main take-home messages here that I would like you to remember. One is that if we want to do this radical paradigm shift, we have to exploit physical space. Essentially, if we want to create a large network of computational nodes, we have to put an instantiation of a node in the physical space on the layout of the chip. We should really go away from this idea of using time multiplexing, where there's 1 or maybe 8 or 32 or 64 cores doing many operations per second to simulate many nodes. If we want to simulate 1,000 nodes, the way the brain does it and the way we would like to do it is to actually have 1,000 instantiations of different nodes. The disadvantage of this approach is that we need to use a large area. You really need a lot of space to put all of these nodes on the chip. The advantage, however, is that if, like in the brain, these nodes are used only sparsely, only a small percentage of any of these nodes is used at any one time, then we don't need to clock through. We don't need to transfer data back and forth. Every node has its own local data. And therefore, we gain a lot of efficiency in terms of power consumption. So this idea of no time multiplexing and co-localization of memory and computation is really crucial for reducing power consumption, which is one of the major problems of today's new technologies. And then, of course, if we want to reduce even more power consumption, we should really try to not abstract away computation with Boolean logic. We should really exploit the physics of the transistors and the memristors and all the devices we have to do computation to the very last, joule. So exploiting the physics for computation is the other important part of this one message of exploiting space. In the next slide, there is the second message that would be of exploiting time. So if you go to the next slide, here, this is the other important thing that is required to make this radical paradigm shift. If we really want to compute like the brain does, we have to give up this idea of time multiplexing, where the computational time is completely decoupled from the physics, from the time of the system we want to simulate or emulate. For example, you can imagine on a computer, you can do weather prediction computations that usually, calculate how the weather changes in hours or days. We can do that in microseconds. Or if we want to simulate complex molecular dynamics that in real life take a few nanoseconds or microseconds, it might take hours or even one whole night of CPU time to do these computations. If we are implementing these neuromorphic circuits, on the other hand, every circuit runs in real time. Time is the physical time. It just the computation evolves through the physics of the devices through time. So this is really completely different from standard ways computers do it. And this would allow us then to basically have a system that is inherently synchronized with the real world events of the data that we want to simulate or to process. For example, if we want to do speech recognition, we could have circuits in our neuromorphic system that have the time constants that are well matched to the dynamics of the speech signal. It's a classical engineering trick of having matched filters. So if we have matched filters, we don't need to make any abstraction. We don't need to time multiplex and have clocks. Everything just runs through the dynamics of the system, which means that, again, we reduce power consumption. So if we can match the circuit time constants to the signal dynamics that we want to process, we have these matched filters that are inherently low power and efficient. And that's what we would try to do. So if we want to process, for example, signals of natural signals, like I said, speech or gestures, motion, we want to measure changes in temperature or vibrations for earthquakes, we have to match the time constants of all of these types of signals to the circuits that we implement in our neuromorphic system. And typically these time constants are of the order of 50 milliseconds, 100 milliseconds, maybe 1 millisecond. But they're in the order of milliseconds, which is very, very slow compared to the standard way that silicon goes. We have to slow down silicon. Instead of going at megahertz or gigahertz, we have to go at 1 hertz or even a fraction of a hertz. It's actually quite challenging to design circuits in silicon that can be so slow. We have to slow down things. But these are the two main take-home messages that I would like to remind you, that you have to exploit space and you have to let time represent itself. This is actually what Carver Mead used to tell us at Caltech when we were starting to do these things. And to give you an example, just a simple example of a circuit, a neuromorphic circuit that actually exploits these two principles, I would like to show you now an example of a recently designed silicon neuron that was designed by Arianna Rubino and just published, a few months ago in IEEE Transactions of Circuits and Systems. This is a silicon neuron which is receiving input currents, analog currents. The currents are being charged up in a capacitor, and then once the voltage on the capacitor reaches a specific threshold, the neuron fires. So this is an integrate and fire neuron, but it's biologically realistic. The leak component of the circuit essentially is implementing a current mode low pass filter, like an RC circuit, that can actually slow down silicon to have time constants of the order of milliseconds with 1 picofarad capacitor, some picoamps here. If you think of it at room temperature, we have 25 degrees, so we have basically 25 milliseconds of time constants with 1 picoamp and 1 picofarad. Those simplify out, we're left with UT. So that's basically how to slow down silicon. Also, once we spike, we actually activate some transistor channels, which are equivalent to the proteic channels of a real neuron. So this would be the sodium part of the neuron. To reset the neuron, we activate other transistor channels with negative feedback. This would be the potassium part of the neuron. And then there's also a after hyperpolarizing current, which models the calcium channels of the neuron. So if you see these small circuits with less than 30 transistors are actually emulating the detailed biophysical properties of real neurons. And in fact, if you show the output of this circuit to a neurophysiologist, it will be very difficult for the neurophysiologist to tell you whether it's coming from a silicon neuron or from a real neuron, for example, in a culture. And this is data measured or actually simulated from this circuit. And what you should notice is the time scales. The time scale is really, as I told you, we slow down silicon to biologically plausible time scales. So we have milliseconds and we have nanoamps on the y-axis. Also, if you have several parameters that you can change, even though the circuit dynamics are fixed at design time, this is an analog circuit, you cannot program it to do anything arbitrary, but there are parameters. So you can change, for example, the spiking threshold, you can change the refractory period, you can change the slope. So there is some degree of flexibility for creating different types of neural networks and different types of neurons, even though the circuit is exactly the same. The table here is just showing you how this latest design, which is now using a 22 nanometer technology node, is also the lowest power that we are aware of. So it's per spike, it's around 14 picojoule with an average firing rate of 30 hertz, which is lower than the other literature we could find, the latest state of the art. So this is to give you an example of a neuron circuit. Of course, neural networks have both neurons and synapses. The neuron is receiving input from the synapses, the currents, it's integrating them, and then it generates voltage pulses, or actually in this case, current pulses. It's generating some pulses. The next layer of neurons down the line in the network will have to convert these pulses back into currents in order to send them to the next neuron. So the circuit that does this conversion from pulse to sort of continuous time current is the synapse, which is in the next slide. And that is essentially the same building blocks that we saw in the neuron. It's essentially an integrator, a current mode integrator with 1 picofarad capacitor. We have picoamp currents flowing, and that's how we get millisecond time constants. And if you see, the output current of this circuit is actually producing the same dynamics of the currents produced by real biological synapses. This below here, this is data measured from a real synapse, and above is data measured from a pair of these circuits. So again, if you look at the time scales, they are nanoamps and milliseconds, and if you look at the time scales of real synapses, we have tens of milliseconds and tens of nanoamperes as well. So that's really showing you how we can build analog circuits that reproduce the biophysics of real neurons. And now we can use these, the synapses and the neurons, to create neural networks. In fact, if you assume that all of the synapses on the neuron have the same dynamics, because this is essentially a first order linear filter, we can use the superposition principle. It's a linear system. So we can actually have one single integrator for many synapses. So this takes up area, this capacitor, so we don't need one per synapse. We can use the superposition principle and have many synapses, like you do have in real neurons or like you have in real neural networks. Each synapse is only a very small circuit with maybe 2 transistors. They all sum their weighted currents up into a single node, which then gets integrated. This would be this green big block here. All of the transistors would be the red blocks. They're very small. They all sum up their currents. Then they're integrated over time in the green box. This continuous current of the green box goes into the neuron that I showed you in the previous slide. And that's how we go from spikes in output to spikes in input to spatially and temporally averaged currents in input to the neuron. And you can imagine you can have many synapses and many neurons. You can create chips that can implement large-scale neural networks. In fact, we can actually not only use transistors, we can use, as I said, these emerging memory technologies that have nanoscale devices that also have long-term memory. They're non-volatile, so we can actually store the weight on these nanoscale devices and then have very dense arrays and very large neural networks. So in the next slide, I can show you an example of a crossbar of these nanoscale devices. In this case, we're looking at a picture from IBM in which there are phase change material memory devices. And you can think of the rows as being the input spikes and the columns as being the lines in which everything is summed together. This would be the spatially weighted average of currents. And then that would go to the synapse, which would then go to the neuron. And this also, all of these devices can either be used as digital devices that have a 0 or a 1. You know, it's either conducting or not conducting. Or you can use them as analog devices that actually implement a weight and maybe can also implement some nonlinear properties. So this is, again, what I was saying, that we have the memory and computation co-localized. We don't have to go and get the weight from some bank of memory outside the chip. Everything is co-localized, and that's how we save power. If we keep everything in the analog domain, we also have some other advantages. So this is the point here. Why should we stay analog all the way? Well, one thing is that if we have analog all the way and we have this principle of time representing itself, we can avoid the use of digital clock circuitry. You know, digital clock circuitry is actually becoming one of the most difficult things to do in large chips, in microprocessors. If you look at the layout of a microprocessor, at least a third, if not even 2/3 of it is actually trying to manage the clocks that's supposed to go at gigahertz across the whole area of the chip. It's really, really complex. It's really power hungry. The other advantage of staying fully analog is that we avoid these large digital to analog converters at the input and analog to digital converters at the output of these crossbar arrays, which have by nature analog devices. These memoristic devices are analog. And these, even though these devices are nanoscale, you can imagine the DAC and ADC converters are actually much, much larger. They're actually microns. And so you would have to waste all the area at the periphery just to have these converter circuits. If you stay analog, you can avoid this overhead. As I told you, if you take advantage of the physics of the analog circuits like the transistors, you can also reduce power consumption. And you can use, for example, analog amplitudes in the weight pulses or analog amplitudes in the duration of the pulse to control the transfer function of these devices. And there are papers from our colleagues that show how you can actually exploit the intrinsic nonlinearities of these devices by modulating these analog pulses. You can use them as intrinsic stochastic devices. If the pulses are weak enough, sometimes they will make the PCM cell switch, sometimes they will not. So you can actually control the stochasticity, the probability of switching by using analog inputs. And you can exploit the non-volatility. So if you give weak enough pulses, maybe the conductance changes, but then it relaxes back to its original state. And this non-volatility property is actually extremely useful for doing complicated learning, spike-based learning algorithms like third-factor learning rules, reinforcement learning rules. In the next slide, I can show you an example. Oops, sorry, I went too much. I can show you an example of, oh, maybe it's not, but I can just tell you there are examples of third factor learning rules that take advantage of the non-volatility properties of the PCM devices to have traces that last for minutes. And so we can bridge across timescales from the behavioral timescale of an agent that is trying to learn, for example, the maze, to nanosecond timescales of the devices that are trying to learn to memorize the weights and keep those for very, very long periods. So these are essentially the advantages of using analog circuits in these types of neural networks. But of course, there are lots of criticisms. There are people that are saying, you know, analog circuits are noisy, they are difficult to manage. Why should we use analog? Why can't we just stick with digital? So I told you some advantages. Now I would like to argue against the disadvantages. And of course, they are noisy. There is no failing this. It's true. These analog circuits are noisy. In fact, in our chips, which have analog circuits, if you stimulate all of the neurons in one core, for example, in one of our chips, the core has 256 neurons. You start injecting exactly the same amount of current into all the neurons. They integrate the current, like I showed you, and then they spike. The time at which they spike is not precise because each circuit is slightly different. There is device mismatch. And then there is a distribution of time to first spike. And this distribution is actually measured here. We can, you know, if we do careful analog circuit design, we can reduce the amount of distribution, but we cannot bring it to zero. There is always going to be some noise and some device mismatch. In our circuits, we don't try to reduce it to zero. We try to actually exploit it. So we typically have a coefficient of variation which is around 10%, 20% at most. But this could be a problem. So the question is, how do you do robust computation by using these unreliable or noisy computing elements? And by the way, also the brain has the same type of device mismatch and the same type of computing elements. So also, how does the brain do it? Well, of course, you all know the easiest thing to do when you have some noise in your system is to average. If you can afford to average over multiple neurons or average over time, then that's the first thing to do. That's the sort of zero order solution to the problem. And as I told you, we have many neurons on a chip. We have, for example, if you have only 4 cores, you already have 1,000 neurons. If you have like 4,000 cores, like the IBM True North, then you have 1,000,000 neurons. So you can afford to average over some number of neurons, and if you do that, that should reduce the coefficient of variation. And this is what we have been doing in the last weeks. Actually, this is very recent data. In our core, we are actually clustering all these neurons in clusters of 2 neurons, 4 neurons, 8 neurons, 16, and so on. And we are taking the average output of these clusters. And if you do that, the coefficient of variation decreases as the number of neurons in the cluster increases. So we can have less noise if we have a spatial average. Then, because these neurons are firing at a constant rate, what we can do is we can count the number of spikes per second over multiple seconds. So we can average over time. And we can average the spiking rate over 20 milliseconds, 50 milliseconds, 100 milliseconds, and so on. And if you average over time, the coefficient of variation decreases as well. So here we go from 18 to 12, from 12 to 9, and so on. Once we know the coefficient of variation, we can actually calculate the equivalent number of bits. So we know what would be the equivalent in bit resolution, just to compare to digital circuits. And it's really nice to see that there is this sweet spot where if you're using a cluster of 16, and even if you average over a very small number, so 20 milliseconds, we have the equivalent of 8 bits. So we can get 8-bit resolution by just using 16 neurons. And we don't have to choose this at design time. We could, in some applications, we could want a 6-bit resolution or a 4-bit resolution. In other applications, we might need a 10-bit resolution. That basically just tells us how many neurons to use and how much time to wait to get the resolution that we want. If you think of it, standard neural network accelerators have fixed point precision, but these number of bits that have to be used are chosen at design time. So it's kind of a disadvantage to do that in the digital domain. So that's one way to solve the problem of resolution. And now I would like to use the arguments of how the brain does it to also address other problems that the community of artificial intelligence is arguing against the use of these analog circuits. So the first, one of the major arguments is that neurons are slow. I told you we try to slow down neurons. What if you want to have fast computation? So this is actually a false myth. This problem that neural responses are slow are there only if you look at single elements, single neurons, also in the brain. In our brain, our neurons are actually quite slow. They take maybe 20 milliseconds, 50 milliseconds to integrate an input and to produce a spike. But we can react with, inside the brain, the reaction times can be of the order of microseconds. Even when we try to understand, where does the sound come from, we are actually calculating the difference in our auditory system with a microsecond resolution. So how is that possible? Then it's simple. We just need to use populations of neurons like we did, since we're using already populations of neurons for averaging. Then we can take advantage of that and we can actually have very fast reaction times. This is data from Tatiana Tumachenko, which is showing you that if you have a single neuron, it might take 20 milliseconds to respond to changes in the input. But if you have populations of neurons, then it can take about 50 times faster to respond to small changes, very small changes in the input. And this is data measured from cultures, from real cells. And you can imagine if we have silicon neurons that have the same properties, then you could get the same type of reaction times. So the fact that neuron responses are slow is only true for individual neurons. If you have a chip, a neuromorphic chip, neuromorphic chips can be very, very fast. Another criticism that is often argued is that if you want to have robust computation and you're using these neurons, then you need to have high rates. Either you need to wait a long time, or you need to have many spikes per second so that you can have precise. I showed you that this is indeed the case for single neurons or for small clusters. But if you think about it, and again, if you look at what the neuroscience literature is telling us, also this is wrong. This is not true. In fact, there are computational studies from Sophie Deneve, Christian Machens, and colleagues that show that if you have a population of neurons, you can train it through learning to encode signals with high accuracy with very sparse activity, meaning that they fire very seldom. There is very low firing rates. And this is a paper showing that, if you have spiking neurons in a population of recurrently connected neurons, you can change the weights of all of these neurons such that they, instead of firing many spikes, which would be lots of these black dots, they fire a very small number of spikes, but they can encode the input with very high accuracy. So this is basically results from theory of spiking neural networks that are telling us that you don't need to have high firing rates, so you can have very low power chips that still can be very precise. And we actually studied these papers, and we made a chip ourselves that is using those learning algorithms. I think I went back and not forward, sorry about that. The next argument that is often made is that if you want to have deep networks and you want to propagate signals across multiple layers in these deep neural networks, then each layer needs to be precise or accurate. You need to have accurate neurons to propagate precise information across layers. Also, this is wrong, and there is a paper from Van Rossum already from 2002 showing you that not only this is wrong, they don't need to be precise, they actually need to be noisy. So if you have noisy neurons, like the ones we have with analog circuits, you can propagate neural activity reliably across multiple layers. And this figure here shows you this would be the signal in the input layer. And if you have precise neurons, only the very strong signals go through at the first layer, and then the very strong signals go through at the second layer, and so on. So by the time you get to the last layer, all the small fluctuations that you had in the input are lost, and only the very large fluctuations here are represented by the spikes of the neurons. If you have imprecise neurons, then the small fluctuations actually are carried across from the first layer to the second, from the second to the third, and so on. And just because you had noisy neurons, but then you take the average of all of these noisy neurons, then you can reconstruct at the last layer what you had at the first layer. So this is essentially saying that not only it's not true that you need to have accurate units in each layer, you actually need to have them noisy if you want to, and then to average over populations if you want to have deep layers. So basically, this is just showing you that we can use neuroscience to convince engineers and computer scientists that using analog circuits and analog devices can work. And that's how actually our brain works. There is an existence proof that brains do that already. And then we can build very low power computational devices with in-memory computing. So this is just to summarize all of these sort of neuroscience facts. Neural responses are not slow if you use populations of neurons. They do not need to fire at high rates. You can have very low power chips, because there are these learning algorithms that show you how to connect the neurons in the right way to get high accuracy. And actually, you need to exploit the fact that they are noisy in order to propagate signals across multiple layers. You cannot have precise neurons like 8-bit precision, because that would lose all of the information if you have spiking neurons. So this is, again, to summarize that if we want to have this radical paradigm shift, we have to look at how the real brain computes, and then we can learn from the real brain and design chips that are very low power and very accurate. So finally, putting all of these things together, I hope I convinced you that it's important to have a radical paradigm shift, and then remembering the take-home messages of exploiting space, letting time represent itself, and then looking at the brain, how to cope with all the problems of analog circuits, mismatch, and noise. There is basically a recipe that was proposed recently by Elisabetta Chicca and me in Applied Physics Letters saying that, you know, you need to basically take the best of both worlds. You need to mix neuron circuits using CMOS circuits. You need to mix neurons and synapses using CMOS circuits, but you need to combine them with the properties of memoristic devices. You need to have in-memory computing, so you need to add capacitors to hold the state of the neuron near the neuron, where the neuron is located physically in the layout, and the same for the synapse. We can use also capacitors for memory traces, for example, for implementing reinforcement learning, but we can take advantage of all of these emerging memory technologies as well. So we can use non-volatile elements for having decaying traces. And then we can have, volatile, and then we can have non-volatile elements for remembering the weights of the synapses for long term. Of course, nothing stops us from combining standard memory elements like SRAM or TCAMs with memoristic memory elements. And we should indeed try to combine the best of both worlds also for what concerns memory. And the communication, I told you, is done with spikes. So we should take advantage of the fact that digital circuits are robust and reliable for transmitting spikes. And then we should also use the tricks that the brain uses to make robust computation. And I showed you some of the tricks, but another one that is really, really important is adaptation and learning. So we in our chips, we always have, in addition to the neurons and the synapses, we always have also learning circuits that can somehow adjust the parameters of the network to perform reliably and robustly. So in the next slide, I try to show you one of the most recent chips that we actually got back. It's using an old process because this was a prototype just to test principles, but it's a chip which we call the dynamic neuromorphic asynchronous processor. It has 4 cores of 256 neurons each. You saw some of the data from it. So we have 1,000 neurons per chip. Each neuron has 64 synapses with 4-bit synaptic weights, so we can actually have a little bit of precision. It has 4 dendritic compartments. It has a lot of dynamics with millisecond time constants and even hour time constants. We can slow down silicon to electrons to flow through the channel with a few electrons per second, so we can get hours time constants. And then we can use them, you know, to do different types of applications. We typically connect them for prototyping to FPGA boards and then to computers or directly to motors on robots. This particular board, we can actually stack multiple chips together. So if we need more than 1,000 neurons, we can put up to 6 of these boards together, and we can have 6,000 neurons. But you know, we can stack as many boards as we need to just increase the size of the network. And we've been using these chips to actually solve real-world problems. So it's not only basic research, but we've been trying to use them in real-world case scenarios. In the next slide, I have examples of papers where we show how to apply these chips. You know, we have the chips, we can connect them to real world data and then have them work as classifiers, as detectors, and produce some output that is encoding the extracting information from the input. We tried with research experiments where we tried to record the neurons of a bird, and from the neural recording detect or estimate the song that was being played to the bird. So we were actually classifying the activity of the real neurons with silicon neurons. We actually connected it to a rat and created a bidirectional interface. So it was like having an extension of the brain, and the rat's intention in the real neurons would be interpreted by the silicon neurons, which would then drive a motorized output. So it was like having an extension of the brain in the rat. We connected it to cultures of cells. So we had experimental setups where there were some cells in a culture in Italy, talking to silicon neurons in Zurich, which were then driving memoristic devices in Southampton. And we had basically a distributed artificial real neural network distributed across Europe through a European project, and so on. You can see there's basically many of these applications are biomedical applications, connecting silicon neurons to either real neurons or muscles with EMG, or detecting heartbeats with ECG, or for example, predicting the location of the epileptic center with high-frequency oscillations in intracortical EEG. So we have many examples, and if you're interested, I could point you to the papers which are shown here. I could actually share the slides. You could just click on these links and you could go to the paper. And just to give you one example of which is non-biological, in the next slide, there's a very recent one that is going to be presented at AICAS, Artificial Intelligence Circuits and Systems Conference, on fault monitoring in industrial equipment with gearboxes. And the idea is that we can use the silicon neurons to monitor anomalies in the vibrations of the gearbox. So we can actually measure from piezoelectric sensors the vibrations in these gearboxes, extract information by filters, and then through a two-layer neural network, a very simple neural network in which there is absolutely no learning, it's just hand-tuned, we can then detect whether there's going to be a change in the standard sound, in the standard vibration pattern, or not. And you can see in the next slide examples of this. So this is an example of healthy gearboxes. We connect the vibration output to the neurons. The neurons have an initial stage where they calibrate, they sort of understand what is the reference levels. And then from that stage on, they are just, everything is normal. Only if there is a defect in this gearbox where we can actually introduce a defect by just changing the data set, you see that the neuron actually starts to fire. So after the initial calibration, everything is fine. And as soon as you have a defect, the neuron starts to fire. And within 170 milliseconds, you can actually alert the user, telling them that their equipment is faulty. This is with one type of data set, which was compared with least square support vector machines, and it outperformed the standard state of the art. With another data set, with real chip data in this case, we can actually even predict the onset of the fault. So we can, with a few milliseconds before, we can actually tell the user, given the sound, we estimate that the gearbox is going to break. And all of this is being done with these spiking neurons, which are, I remember, if you remember, we're burning picoamps, nanoamps with 1.8 or even 1 volt power supply. So the overall power consumption of this fault detector is estimated to be around 200 microwatts at most, which is a factor of at least 1,000 less than what you would have if you had a GPU, even a portable GPU or low power GPU programmed to do the same type of task. So this brings me to the conclusion. The last slide, or just in time. This is just to say that these types of chips are actually not supposed to replace standard GPUs or architectures. They're supposed to complement them, and they're actually useful only where you need low latency and you need low power. If you have all the power you need, there is no sense in using these chips. But it's also useful where you can connect directly to the sensor. If you have to take data from a laptop or a USB stick, then the power is being burned just in the data transfer. Only if you can connect these types of chips directly to the sensors, then it's a promising technology. Otherwise, if you need to do any type of number crunching, matrix inversions, matrix multiplications, then standard technologies are also still very good. So the idea is that these types of applications, these brain-inspired circuits, are meant to complement and not to replace standard approaches. And yeah, as I said, this was kind of the last slide. This is just to summarize the conclusions that it's really a good time now to start studying these things, because conventional AI has some serious limitations in terms of power requirements, and the standard approach is not sustainable. Nature even had a paper in 2018 saying that this was a problem. New emerging memory technologies are coming out, and they need to have analog circuits to process them. Neuroscience has made tremendous progress, and it's telling us how to use neurons and synapses that are noisy and faulty, like the ones we have in our brain, to do robust computation. And so if we put all of these things together with the recipe that I gave you, this is the perfect time to start following this neuromorphic engineering approach and try to build microwatt devices that somehow complement and maybe can, in some cases, outperform these, hundreds of watt devices. And if you think of the difference in terms of power consumption, it's essentially the same that you have with a Swallow and a jet and a Boeing 737. So it's really some elegant solution that in some cases where you have sensors and sensory processing can really outperform conventional approaches and hopefully solve some of the power requirements that standard technologies are starting to face. And this was really the last slide. I'd just like to point out that there is a really talented set of students that has been supporting all of the work that I described, the postdocs and the PhD students, and of course the funding agencies that have been paying for all of the research, including startups. There is a nice startup that is starting to sell these types of chips around the world, has been also supporting the work. And of course, I'd like to thank you for your attention and apologize for the delays that we had at the beginning.
Thank you very much, Mr. Professor. Impressive, impressive. Of course, there are a lot of questions. One question I have is, now you are playing with the currents of the order of 1 picoamp. In the current technology, this current, it's not, is it possible to control such a small current? Because it's below noise.
Yeah, it's a very good question. In fact, if you saw, it's a 180 nanometer process. In that case, the leakage currents, it's with XFAB, so it's optimized for analog design. And in that case, the leakage currents can go down below maybe to 2-3 picoamps. So if we have 10 picoamps, we're a little bit above the noise margin, but still we're very close to the noise margin. With the 22 nanometer process, you would think it's much worse, but actually we're using fully depleted silicon on insulator technology, FDSOI. In that case, the leakage current is much smaller, below 1 picoamp. So we can actually take advantage of this FDSOI technology for having very small currents.
And it is also very much related to temperature. Of course.
Yes, that's the other big problem. There are a lot of temperature dependencies. The way nature solves it, like is through learning and adaptation. So we need lots of negative feedback if we want to have robust computation in face of temperature changes. But of course, we can also use engineering techniques. So we do have bias generators on chip, programmable bias generators with GTAT and GTAT and ITAT current and conductance temperature compensated circuits that somehow try to keep everything in the right range.
Thank you very much. Another subject which you mentioned a few times, and we are very interested on that, is about memory stores. We know what is a memory store in theory, but we don't have many practical examples. Can you have some phrases maybe on what the technical and the real data you have so far on this?
Yes, I actually was brought into this field of memoristive devices about 10 years ago from Themis Prodomakis. He's a professor at Southampton who was one of the first to start investigating the use of these memory devices for neuromorphic. There are actually very different flavors of memoristors. There are some that are based on phase change materials, which is a very well-established technology. It's actually the closest to market. IBM is very strong on it. And that is basically, it's the same trick used on DVDs. You go from a crystalline state to amorphous silicon state, and depending on the state, if it's crystalline, it's low conductance, and otherwise it's high conductance. And that's one type of memoristor. Other types of memoristors are so-called oxide-based resistive memory devices, which are essentially pieces of material like hafnium oxide of 10 by 10 by 10 nanometers. Sorry, I'll close the door. which in these 10 by 10 nanometers, if you give enough voltage, you actually move ions, and by moving the ions, you create oxygen vacancies, and then you change the conductance in a permanent way. It's really changing the physical structure of this material. And then the other devices are ferroelectric devices. In that case, it's not moving ions around, but it's the same principle. By changing spins or poles, you can change the conductance. And finally, the last one that I know of is spintronics. It's also devices in which you change the electronic spin of the devices, and depending on the polarization, they have higher or lower conductance. We don't do any of the research directly ourselves. In Zurich, we actually collaborate with colleagues. A few years ago, it was still very, very basic research, but now it's becoming accessible. We basically, what we do is we design whole wafers with XFAB. Then we send the wafer to our colleagues in Southampton, in Jülich, in France, in Cialetti. And they basically, through post-processing, deposit these devices on the top metal layers of vias that we have. And that's how we can connect these two terminal devices to our circuits. And then we can have memristive CMOS neural networks. So it starts to become common, but it's still very, very much an art. And I should tell you, it's also very frustrating, because whenever people tell you that they have memristive devices, there is a huge mismatch, much more than in transistors, and a huge number of faults. So in a 1K array, maybe only 10% of those are actually working, and all the others are not. So it's still quite difficult to get a full-blown spiking neural network chip work with memristors. But we are actively investigating this area.
Thank you very much. Mr. Professor from Romania, please ask questions.
Mircea Boda. My name is Mircea Boda. May I ask you about numerical value? In the instruments for bearing measurements, noise bearing measurements, what is the noise floor level? Do you know? Maybe it's very particular, this asking.
Yeah, so when we characterize our chips, we do have to use very precise measurement instruments. So we're using Keithleys that can go down to fractions of picoamperes, maybe even 10 to the minus 14. I would have to look at the specs. And then the noise floor for doing robust computation in our chips is really limited by the leakage current, so the dark current of the technology. And as we were discussing before, this is of the order of 3 to 5 picoamps, and having voltages of maybe a few hundred millivolts, then one can find the equivalent signal to noise ratio.
Yeah.
And what really, in the end, what it really is the limiting factor is this coefficient of variation, so the mean over the standard deviation. And in our case, we have to cope with values that can go up to 20%.
Thank you very much.
Questions, please?
Excuse me, do you hear me?
Yes.
Well, my name is Liviu Goraș from Iași. Will you make some comments relating the fact that you spoke about deep neural networks, which means training weights and spiking neurons?
Yes, so
because in fact, training deep neural networks means arranging the weights in order to do intelligent scalar products. And in the same time, you are speaking about spiking your neurons. If I understood well, the input is not an image, but it is a time signal. And the time signal in deep neural networks, I do not know how to manage.
Exactly. So we do talk about neural networks, so the terms are the same, but it's really like talking about apples and oranges. The standard deep neural networks have been developed so far, at least originally, to process images, static images, and whereas spiking neural networks are ideal for temporarily changing signals, like I make the example of speech, but also biosignals, the heartbeat, EMGs, neural activity. And the most, as I said, one of the most important features of neural networks is learning. But also in the case of the deep neural networks and spiking neural networks, there are quite different algorithms for the learning. In deep networks, the standard algorithm is backpropagation, so doing gradient descent and finding the weights that are optimal for doing the perfect matrix multiplication operations. In spiking neural networks, it's actually still a very active area of research in computational neuroscience and in theory. There are many papers coming out essentially every week showing how to approximate backpropagation with spiking neural networks. So there is one line of research that is trying to copy or take from deep network theory or deep network algorithms the ideas and map them onto spiking neural networks. And as I said, there are several papers coming out on arXiv essentially every week for approximating backprop with spikes, which is quite difficult because spikes are nonlinear and you cannot do a derivative, so it's very difficult. Another line of research is again going back to the brain and looking how does the brain do it, because we clearly learn and we have spiking neurons inside our brain. And so there is also a vast body of literature from the computational neuroscience that is using spike timing based learning algorithms, so-called STDP, spike timing dependent plasticity, and variants of that for implementing learning in spiking neural networks. And at some point, I imagine these two lines of research will converge. And then anything that can be done in biology is also easy to map in neuromorphic circuits, because we have the same problems with our silicon neurons. They only have access to local signals, to the input and the output, but there is no global parameter that they can access to through DRAM. And they can only do very simple operations. They cannot do matrix inversions, so they can basically increase the weight depending on the delay, on the time. They can do basically these STDP type of algorithms or mechanisms easily. And so this whole field depends on the convergence between theoreticians, neuroscientists, engineers, and maybe even if we want to use the memristers, material scientists. It's still an active area. It's still not solved. It's still very, very intriguing and challenging, but it's really fun to work in it.
Should I understand the fact that the class which is possible to be considered for inputs in spiking neural networks is much restricted than in the case of classical neural networks?
To really exploit the features of these types of chips, it's best to use time-varying signals. But I wouldn't say it's restricted. There is lots of time-varying signals that one could try to classify and have edge computing products or applications. For example, looking at how the environmental signals change, whether it's smog or traffic in smart cities or vibrations in mountains to predict avalanches. In addition to all the sort of health-related signals that one can get from the body, whether it's heartbeats or sweat or temperature. So there is a lot of opportunities for creating products that do not need to process images. Also, for example, in refrigerators to measure humidity, odors, smell, gas concentrations. There's a huge market, I would say, for signals that are not two-dimensional, that are time-varying, that can be processed by these types of devices.
Okay, thank you very much, and congratulations for this very much.
Thank you. Thank you. It's a pleasure.